Hello, in this video I'm going to derive an expression for the gradient. So that is grad of some scalar function phi. Phi is a function of arbitrary coordinates x1, x2, and x3. So I'm going to start with an arbitrary basis set. So we'll call this one x1, call this one x2, and this one x3. They have unit vector components e1, e2, and e3. And so given some point, we'll call that x, I want to know what the change, the infinitesimal change is when I go to some other point, x plus dr. Now, we can obtain an expression for the metric being ds squared is equal to h1 dx1 squared plus h2 dx2 squared and h3 dx3 squared. Now let's say I want some infinitesimal, let's start with a small vector, delta r. Now delta r is going to have length components, h1 delta x1, pointing in the direction e1, h2 delta x2 e2, and h3 delta x3 e3. So I'll change this d to a delta, and then we'll take the infinitesimal limit as delta goes to d. So I'm going to split this up into components. So we're used to taking grad phi in Cartesian coordinates, and that will tell us, that will give us a vector, usually that has 3 components. So in Cartesian coordinates it ends up being del phi, del x1, del phi, del x2, del phi, del x3, where x1, x2, and x3 are just x, y, z. But now we're trying to generalize it to any orthogonal coordinate space. So we need to take into account these scale factors, and what they do is basically make sure that all our units here are the same. So if x2 and x3 happen to be angles like theta and phi, those don't actually have a length scale. We need to multiply them by some factor to make sure that we're talking about the same units. Now, to derive grad of some scalar function phi, we'll start with the x1 direction. So we want to know the difference in phi given some small change in phi in the x direction. So we want to know what phi is at the point that we're trying to get to. So that's phi evaluated at x1 plus h1 delta x1. That h1 is there so that we're sorry, no. We're just going to say plus delta x1 and x2, x3, because we're assuming we don't move in those directions. We're going to subtract that from our scalar function evaluated at our original point to find the difference in those two scalar values. And then we have to divide that by the length that we traveled. And that is going to be the length. We need to take into account that scale factor, h1 delta x1. Now, if you've done some calculus before, you'll realize that this is the definition of the partial derivative. And so if we let delta x1 approach dx1, we're going to end up with change in phi divided by our change in x1, and that's going to be multiplied by 1 on our scale factor, which is from that part there. Now we can repeat this with all of our directions, x1, x2, and x3, and we'll end up with a vector that we are looking for. So this term right here is a vector pointing in the E1 direction. We'll also get 1 on H2 del phi del x2 plus pointing in the E2 direction plus 1 on H3 del phi del x3 pointing in the E3 direction. And this defines grad phi. Now this will work in any orthogonal basis, whether it's cylindrical, spherical, you may even have more dimensions than 3, and that is what we were looking for.